Welcome back, everybody. I got to do the announcement of voice part for the video. This is Calculus 2. We are looking at two sections today, 6.4 and 6.5. 6.4 is on the finding the length of a curve, which is kind of neat. And 6.5 will take that curve and we will revolve it around an axis, just like we did in previous chapters, and then we'll do surface area rather than volume. So we got some curve here. Y equals f of x. And it could be like as crazy curve as you want. It'd be nice if we could just like lay a string on it, pull it straight, measure it with a ruler. And in some cases you can, but in general, no. So what we're going to do is we're going to slice this up into tiny pieces. I'm not going to make them not so tiny for pictorial purposes, but we slice them up into tiny pieces, each with a width delta S. S is what we use for arc length. You know that from trig, if you took trig. S equals r theta on a circle. And so we what we're going to do is we're going to eventually we're doing the limit as the number of delta s's, the number of them goes to infinity. So that delta s turns into a ds. So the pieces get smaller and smaller and smaller, just like we have done with everything in calculus. But we start with the bigger picture. And so we got point A to point B on each one. What we do is we make a triangle. So I'll blow that up a little bit. So this is going to be my ds. This is in the x direction, which is dx, and vertical is dy. This is clearly a right triangle. Now, granted, the formula we're going to use the Pythagorean formula. So ds is not the red line, but it's close. Well, I'm going to say delta s is not the red line. But as we make delta s super duper duper small, ds is approximately the red line. So we can approximate this with Pythagorean's formula. So we'll say ds squared equals dx squared plus dy squared. And generally, we like to have make this into something useful. We'll divide by dx squared on everything. And I'm going to factor out the square part. So this is ds dx squared equals 1 plus dy dx squared. This is such a simple way to find it. And when you do it, you're like, wow, or maybe you would have thought of it, but I would never have thought of taking this approach to doing this. We'll take the square root. Hit that bad boy with the square root on both sides. And we get ds dx equals square root of 1 plus dy dx squared. But I want s, not ds dx. So what we're going to do, let me wait a second, let y'all catch up to the magic. wonder. If we integrate this with respect to dx, this left side becomes s. So we have s equals a to b, the integral of 1 plus dy dx squared dx. There are other forms of this equation too. Because I divided by dx, because I wanted to do a dx unit later on, but if we wanted dy, if we were going to integrate vertically, the integral version of this, I'll put c to d, integral of 1 plus dx dy squared dy. This is cool shit. No one looks like, ooh, ah. Like, I can found the length of a curvy thing without a ruler. What the fuck? That's magic. Y'all need more wonder. And then sometimes when we parameterize stuff, I don't remember if you know, do we cover parameters in our parameterization in Calc 1? I don't think we do. If we decide to say X and Y are functions of time, like it's a position thing, you're like a car driving down up a mountain road, and your position X, Y is changing with respect to time. So like X of t, Y of t. Then we can do like T1 to T2. And here we'll have a dt now. And now both of them are present. Yeah.
So beyond this, the integral DC and 1 plus dx, that's just a different version of that.
Which line? What are you talking about?
Like from the S equals integral and the.
These are so if I had done this whole process instead of dividing by dx, done dy, I would get this. And if we had the positions of x of t and y of t and we went with dt, we would have this. So they're just 3 variations, but they all look very similar. And they're created the same way. This one is for, this is a parameterized curve. And these end up being called parametric equations. And we'll do an example here so you see what I'm talking about. I think we're just going to shove you straight to the deep end. We're going to go with the hard problems right away. None of that. Just footing around, doing easy shit. Do the hard stuff. That way, the easy stuff on the homework feels really easy. Make sense? The alternative is do the easy shit in class and you have the hard stuff for homework where there's no teacher with you. This is a good strategy. Does anyone need this up longer? Okay, I don't see anyone saying yes, so we will proceed. Ooh. All right, so our first example, is going to be, we're gonna find the arc length of f of x equals 1/12 x cubed plus x to the -1 along 1 is less than or equal to x less than or equal to 3. I'm going to go ahead and say, fuck graphing this. Is anyone okay with that? Because I don't know what that's going to look like. I can get x cubed pretty well, but that 1/x, adding it to it, just really kind of throws shit off. Not a whole lot, because it doesn't get to be a very big value, but still. So we've got f of x. We're going to do along, I'll rewrite the formula real quick. We're doing a to b, square root of 1 plus uy dx squared dx. And that's like f prime of x in there. It's okay if you didn't appreciate the magic of how this created. I don't think I did when I was a student. I was just like, fuck, more formulas. Am I right? If you're crafty, you remember you can rederive the equation or formula from the picture. I've had students do it with spherical coordinates in Cal 3, and they have ugly equations. All right, so y is 1/12 x cubed plus x to the -1. So our dy dx is, we bring the power down, we got 1/4 x squared minus x to the -2. So rather than trying to cram this all underneath that square root and deal with it then, let's figure out what dy dx squared is first. Looks like we have a 1/16 x to the 4th. We got a minus of 1/4 and minus another 1/4. And then plus x to the -4. So this will be like a 1/2. My integral will be square root of 1 plus that. And we're doing x from 1 to 3. And you might be going, holy fuck, how the fuck are we going to integrate that? Well, it's going to be easier than you think. If we clean this up, I'm going to add the 1 to the 1/2, and I'm going to leave it in between them. Kind of like the minus 1/2 was there before. Because I added this 1 to the -1/2. That's all I've done so far. Added that one to that, and we put it here in the middle. Because this was I'll put the -1/2 right here. That's -1/2. Now, doesn't this look a lot like this? Other than this sign right here? Is it possible that that's, or there's a reason for that? By making it ending, or by having it end up being positive, this ends up just being, I can split this into 1/4 and 1/4. And now I have the positive versions of this, which makes this positive in here. And I just end up with 1/4 x squared plus x to the -2, that quantity squared dx. Now, if you don't believe me, you could. I'm going to show this on the side. You could factor out. Let's see. I'm going to pull out a 1/x to the 4 there, and this becomes 1/16 x to the 8 plus 1/2 x to the 4th plus 1. And you could do some like u sub on the x to the 4th, see how it ends up being, that this ends up being a perfect square. You could show this with the u sub. But if you're willing to accept that that is what that is, just to change the signs, because it looks a lot like this right here, just a different sign. Good. Which means this becomes the absolute value of 1/4 x squared plus x to the -2 dx. But that's what happens when you cancel a square root and a square. But our x's are positive. We don't have anything being subtracted. Everything's going to end up being positive in here, so I don't really need the absolute value signs, do I? Does that make sense? X is positive from 1 to 3. So that means x squared and 1/x squared also are. So everything inside of it is positive, and I don't need an absolute value sign. I'll rewrite it without it, but if you skip rewriting it without it, I'm okay with that. And now we're integrating. Go up the power, divide by the power. We got 1/12 x cubed. Up and divide, we got minus x to the -1. From x equals 1 to x equals 3. And now we're just evaluating. Hey, there's no 1/12 on that one. There we go. So 27/12 minus 1/3, that would be 4/12. Minus 1/12 plus 1, I'll make that 12/12 so I can combine them. I get 34/12, which is 17/6. Any questions? Yeah, the problem looked really screwed up. The function looked really screwed up in the beginning, but it was tailored to have a nice, clean outcome and still like test some stuff for you, show you how it works. Is ready for another? Okay. On this one, we're gonna do x equals 1/8 y to the fourth power plus 1/4 y to the -2 power. And we're gonna go from one is less than or equal to y, less than or equal to 4. And I'm gonna let you guys work on this. You guys work with each other for a little while if you want, work solo. You do want to do like a dy here. So square root of 1 plus dy dx squared dy. Give it a try. Again, feel free to talk to your peers. Hopefully you guys have found the basis in it by now. What? We want to do, oh. Thank you.
I thought I was looking to set the other one, but one of them minute first.
No, fuck that. Wrote the wrong damn thing. You just write dy dx so much more. Like writing dx dy feels awkward.
With the X. But the X.
You'll get used to that one. In fact, dx dt and dy dt, you'll get really used to it because anytime you're doing stuff in like physics or engineering, t is time and like that's you're very much looking at what changes over time.
Yeah, and you build it up at this sort of like, you go right X, no, X doesn't belong on the bottom.
Right. In fact, dt is I think more common than dx in physics. Maybe not engineering, but physics. Okay, so it's definitely doing chapter 11 in order. Like one, point one, point two, point three, point. You'll see spherical is like 7 or 8. I move it up to right after 1 point when you get all that graphing, and learning how to draw out of it early. Sure everyone's getting the same dx to y. Otherwise, this shit's gonna get hard real quick. Bring it down, you're gonna have a 1/2 y cubed minus 1/2 y to the negative 3. I can't blame you for wanting to pull the calculator out at the end if you guys are doing that. I resisted. Now, I don't know if I'm correct. We'll find out if you get the same thing. But if you're done already, I got S was 32 and 7/64. If you have a decimal version, I don't know what 7/64 is. It's got to be less than 0.01 or 0.02. It's 32.01 something. Well, then there's a 7 on top, so maybe 32.1-ish. Is that about right? What is that decimal, Dad? You just had it on your, oh, you got it written down, yeah.
No.
Sounds right. Yeah, I was pretty close with the 32.1. That's some good estimating right there. Did it? Not too bad, is it? Doable. So long as the integral's doable. You're like, fuck, something squared under a square root. I don't know about this, looks shifty. They kind of really, until you have like the difficult, I don't know, let me not say difficult, the more complex integration patterns. There's only so much we can do. This would be so much more fun if we did integration by parts before this. Ainsley doesn't like integration by parts. Do you? I thought you didn't like it. Oh, you did? So don't put words in my mouth. Oh, my bad. All right, I'll start doing it. If you're still working, keep checking along. Check up every once in a while, see how you're doing. I'm getting 1/4 y to the 6th. And then this is 1/4 and another 1/4, like minus 1/2. And then plus 1/4 y to the -6. So that's dx dy squared. I'm going to add the 1 to it here before I put it in the integral. That'll slip right in the middle again, and we can see that this should become 1/2 y to the cubed plus 1/2 y to the -3. So that's 1 plus dx dy squared. So we'll put that in the integral. We're doing from 1 to 4. Squared. Oh, I'm missing a square there. There we go. And then we have dy. This would again normally have the absolute values, but these are all positive terms. So I'm going to skip it. I'll just write absolutes not needed. Because y cubed and 1 over y cubed are positive for 1 to 4. We have no negative numbers, so there's no way to introduce a negative number into this. We integrate that bad boy, and we have 1/8 y to the 4th minus 1/4 y to the -2. Evaluated from the 1 to 4. A lot of times we do this full thing at 4 using 4 minus the full thing using 1. I'm going to show you guys another way that you guys are comfortable with calculus. We can easily do this with just the first one here, 1/8, and then we'll do the y to the 4th term from 1 to 4 at once, minus the 1/4 y to the -2, do the 1 to 4 here. That way you have all the shit that has this similar powers next to each other. 1/8, 4 to the 4th, minus 1 to the fourth minus 1/4. This is 1/4 squared. Oop, that's a 1 there. Minus 1/1 squared. When you distribute this, you're gonna end up with 1/64 here. A bunch of shit cancels out. Nope, you get 60. You get 32 there. Am I saying? Minus 1/8. Minus 1/64. Plus 1/4. And when you clean that all up, you get 32 and 7/64. This would be minus 8/64. The other way of doing this is obviously with the 1/8 4 to the fourth minus 1/4 times 1/4 squared. And then we'd come over here minus 1/8 1 to the fourth minus 1/4 times 1/1 squared. This is the way you're taught. This is the taught way. In fact, that's what I did when I got my answer. I just felt like showing you guys another way. You guys ready for more? Yes. How far up? 1 plus. The 1 got added to the -1/2. Became positive 1/2. That one? That's part of the integral. So I was just calculating what goes under the square root. Outside of like, because otherwise you're rewriting the integral every single time. It's easier just to find out what that is before you put it in the integral. So you're not having to rewrite a whole bunch of shit that's unnecessary each step. Does that make sense? It'll save you time and paper eventually. Time is the bigger issue. Well, there's no reason any teacher should be upset with this process. Like, there's nothing that is wrong here.
Yeah. I don't know, I got marked off half a point on estimates because I had a fraction here, I was going to find another fraction, and there was only parentheses around one set of fractions. Instead of both sets of fractions.
Depending on how bad it is, I generally will ignore like minor shit. As long as it's clear you did the right thing and drop the parentheses. You'll notice I'm doing the parentheses, even when I stick it in the integrals. Every time I've done it, I put everything in parentheses every single step of the way. Because I am trying to make sure that I show it the right way. But it's very easy to not put parentheses here and just put the line with the 1 to the 4 at the end. Having the parentheses there kind of makes it a little clearer, like what's going on here. I'm kind of like distributing that to get down to here. It actually makes doing the math part easier, I think. Yeah. Or they'll have a simpler form already. You'll be able to integrate. These started off with fucked up functions. So, like on like a test, I'm probably not going to have a fucked up function. Or if you do have a fucked up function, it's going to be one you've seen and done before. I'd ask Ainsley what she's generating for practice for you guys, and maybe think about using those on the test. And then you guys might flood her SI. Keep her busy. You wanna help me make the test, Ainsley? Sounds like what we're doing. Anyone need that longer? Okay, we got one more, before we take a break. And this is gonna be, you guessed it, functions of T. Oh, and we need Y. And we'll do this from 0 is less than or equal to T less than or equal to pi. So as a reminder, this is what we're looking for on the setup. T1 to T2, square root of dx dt squared plus dy dt squared dt. So let's just start taking derivatives. Take a derivative with respect to t. Derivative of cosine is negative sine. Oh, what do I do with t sine t? Anyone remember? Product rule. So I'll take the derivative of the first one. I'll write it out on this first one. T prime sine t plus t sine t, derivative on that one. That's just a refresher on what the product rule is. If you jumped straight to plus sine t plus t cosine t, that's fine. So dx dt is actually kind of nice. It's just t cosine t. And y will do dy dt. That's cosine t. Minus, we take the derivative of the t first, that goes away, we have minus cosine t. And then we take the derivative of the cosine, we get a negative sign that makes a plus t sine t. So dy dt ends up being just t sine t. So dx dt squared is t squared cosine squared t. And dy dt squared is t squared sine squared t. So we're going to do S, we're going from T1 to T2, which is 0 to pi. We're going to have the square root. I've already done the squaring portions, I'm just plugging these in. So t squared cosine squared t plus t squared sine squared t. DT. You get good at this stuff. It's generally gonna be like after or around March 14th, we do an integration B in FNL, Friday Night Lab. There's cash prizes. Me and other teachers kick in cash. And you're just practically doing integrating. There's never calc-free material in there, but it's usually a lot of fun. People walk away, have a good time, make some money. Some people make some money. All right, what can I do? Factor out the t squared. I like that. That sounds like a plan. T. Now what? It is. That's one. So we're looking at, before we deal with the square root and the square root of t squared dt. And you know what? Since it's not going to take a whole lot of room to do the absolute value because it's a small thing, I'm going to do the absolute value just to remind you it should be there. But on 0 to pi, t is positive the whole way. So we can drop the absolutes, and this is t dt. You didn't think that was going to clean up from that, did you? No. They're very much tailored to make nice, get past the hard shit to have a nice simple integral. So we have 1/2 t squared from pi to 0. So pi squared over 2 minus 0. And it just ends up being pi squared over 2. And let's take a 10-minute break. In fact, I'll stop the video and do a new video for the 6.5.